Alright, we're back for, this is Dr. Calkins, we're back for week 12, chapter 10, Electro Chem. This time we're going to stem off of our previous lecture with oxidation states and show you what oxidation states can tell you with oxidation and reduction reactions. So this is typically single replacement, it could be combustion. Single replacement has to work with a more active metal. We'll talk about that briefly today, but it's also in lab. But also look for combination and decomposition. The only one that we're not going to expect to see is double replacement. See double replacement, throw it out the window. It's an ion reaction. It's not an electron transfer reaction like all the others. So a couple rules to remember here when we talk about oxidation reduction. We have the ability to remember this with a cute little mnemonic of Leo says Gur. So hopefully Leo in this case is a lion, whatever. So Leo says Gur. This stands for loss of electrons is oxidized or oxidation. Gain of electrons is reduced or reduction. So in order to be oxidized, you're going to have to lose electrons. So in your reaction, you're going to have something lose electrons by kicking them out. That's going to be a loss. So they're always going to be after the reaction arrow. And then Gur is going to be the reverse. The electron's going to come into this reaction and a gain. That'll be in front of your arrow. So this will be like a capture that we saw in nuclear chem. In a sense, it's just not going into the nucleus, it's going into the valence electrons. And here this loss is going to be loss of electrons from the valence to somebody else. So if you're oxidized, or if you're reduced, that's the R versus the O of the idea. But here's the tricky part. If you're oxidized, you're also the reducing agent. Because if you're oxidized and losing, that's going to force somebody else to gain. If you're forcing somebody else to gain, you're forcing them to reduce. You're the reducing agent of whoever's gaining. So you got to be careful. Those are very similar but different. If you think reducing is reduce, you're going to get it wrong. It's backwards. So if you're an agent, just think opposite, like a spy movie. As soon as you hear the word agent, think opposite, and oxidize would be the answer. Same thing is the case over here. This is the oxidizing agent. And again, think agent, think opposite. If you think oxidizing agent and oxidize are the same, they're opposites, you'll get those wrong half the time. So be careful. If the word agent in there is there, reverse it. If you're losing electrons, you're going to be negative. And if you're losing electrons, if you're negative, that's called the anode of a battery. If you're gaining electrons, you're typically positive, and cats have paws, or in this case, cathode of batteries. You'll see that in this chapter briefly as well. So when we think about these reactions, we just need to practice who's the gainer, who's the loser for lots of reactions. Let's try one with our little reference here fairly close. If we just think of something simple like water. Water can break apart, decompose into hydrogen and oxygen gas. So we have, to balance this reaction, for practice, this is decomposition, it's got one reactant. So notice we have two H's, we have two O's, we're going to put a 2 here and a 2 here. That balances the equation. Gives us 4 hydrogens and 2 oxygens on both sides. But what this chapter is about is what happened to hydrogen before and after. What happened to oxygen before and after. So these are called half reactions because it's telling half of the story of what's going on. We have these oxygens and we have these hydrogens. What happened to them? Well, rule 1 from our earlier lecture says that elements have no charge. So over here, these guys have no charge. They're elemental atoms. Over here we have 2. Sure, this happens twice, but that's less important. Even if you forget to balance these, it's not going to change the answer in Intro Chem. It's important for Gen Chem to do that. It's useful in Intro Chem to do it, but not necessary. So how did hydrogen become neutral? How did oxygen become neutral? Well, when you think of this one, like we did in that earlier example, we found that hydrogen's a positive 1. Take that twice, you get a positive 2. Oxygen's a negative 2, and they balance. So we can use oxidation states to figure out how this happens. So we're using both lectures at the same time. So we have a positive 1 for hydrogen, that's what we expect, and a negative 2 for oxygen, that's what we expect. So how did a negative become, or how did a positive become a 0? How did a negative become a 0 is what we're after. So maybe you don't know, so maybe you guess. Maybe you just throw electrons in front, see if it's a loser or a gainer. In this case, it would be a gainer if it works. Will a negative and a positive make a zero? You would say yes. Negative and positive cancel. So since electrons are negative, and this is two positives, this would be two negatives, but even this 2 and this 2 doesn't change the answer. What's important is the electrons are in front of the arrow. If the electrons are in front of the arrow, that means they were gained. So we aren't looking for products as answers. In your homework it'll be A, B, C, and D. We're looking for reactants because they're the ones that give up the electrons. The only time we look at products was 2 chapters ago for double replacement, because that's where you can find spectator ions and that's where you can find precipitates. But here it's reactants only. So hydrogen plus 1 is the GUR. It gains electrons and is reduced. It is also the oxidizing agent. So there's one of our answers. Once we know one, we get the other for free. This one's going to be oxidized and the reducing agent. What's unique about this scenario, though, is oxygen, if we were to put electrons here, notice negative and more negative will never make zero. That tells you, if by chance you were to put electrons over there, that the math would not work. Here it takes electrons out so that negative and zero can make negative when you do the addition. The arrow's like the equal sign. So this is 2 times a negative 2, that's like a negative 4, so you're going to take 4 electrons there. Doesn't change the fact that this is a gain, that this is a loss of electrons. It's after the arrow. That's your Leo, after the arrow, you're oxidized, and the reducing agent. So you're causing reduction of hydrogen, you're causing the oxidation of oxygen. This reaction is reversible, so you can make hydrogen and oxygen go into water, so it can go the other way as well. But in its current format, these are the answers there. Let's try another one. This was a decomposition reaction. Let's try a single replacement reaction. So here's iron and copper nitrate. That's going to produce iron nitrate. We'll assume that it's a 2 to make it easier to think about, plus copper. So let's zoom out just a little bit so you can still see everything at the same time. We have an iron, we have a copper, and then we have this nitrate ion, but because it's nitrate before and after, we'll save you some time. That's what we call a spectator ion. The reason this reaction works, if you're married to copper, would you rather be married to iron? The only way to deal with that is to deal with the activity series. So find copper, way down here, terrible partner. Find iron, way up here, that's going to work. So as you look at this table, notice what it tells you. It says loses electrons the most easiest. This is the best Leos. These are the best losers. These are the easiest to oxidize. That'll help you in your homework. So easiest to oxidize is up. That means easiest to reduce must be down. These are the least likely to lose electrons because they're the most likely to gain electrons. So the worst partner to have, go figure, is silver, platinum, and gold, so to speak. So as we look at this, we know it's going to work because we are marrying up in our home record kind of analogy. Let's just think about how this happens. Iron is by itself 0. Copper ends up by itself 0. If we reverse these charges, that's a little faster than calculating its oxidation state. This is a +2, this is a +2. It's pretty easy to see that they switched. So who's the Leo, who's the GUR? Well, again, if you're not sure, just throw electrons in. Does negative and 0 make positive? Heck no. But 2 negative and 2 positive, 2 negative, 2 positive will make 0. This is a loss. Iron is oxidized and the reducing agent. Never choose products ever. Where do those electrons go? Those electrons go to copper. So if you put those 2 electrons here, give them the copper. Copper is -2 and +2 become 0. This is a gain, this is a GUR, and that's reduced. R for the GUR of reduced, and the opposite agent, so oxidizing agent. Those are the answers we're looking for. So as you do this, just think about where do those electrons go before and after. It'll work for any combustion reaction, any single replacement reaction that actually works if you're picking a more active metal. It'll work for most combination and decomposition reactions that actually transfer electrons, not all do. It will never work for double replacement because those are ion reactions, not electron transfer reactions. So this should give you enough practice along with the lab itself that practices a whole lot more. And this will wrap up chapter 12. See you next time.